if it was measured like right here. But if you actually take a measurement from here, because the optics, this is the ultra low 7 lumens, okay, because the optics are making this ring right here, this donut hole in the middle and everything, this is not an accurate measurement. Okay, and so it's not, so if I measure it from 1 inch, okay, I'm not going to have 2 or 3 million lux because it has not fizzled out into the spot that it's supposed to be. Okay, and we'll talk more about that when we get to myth number 2. In fact, we'll talk more about that in a different video when I explain how to properly measure candela. It's the same as throw. Throw is measured after measuring candela. You measure your lux from a farther distance away, like 10 meters. You calculate that back to 1 meter. That gives you your candela, and then the candela to distance is a very simple algorithm. And I don't know the calculation by heart, but it's really simple. It's like it's a root. It's a square of the root, or something like that, or square of the cube of the square, or something like that. Okay, and basically it's based on how much intensity reaches out this far. And in this case, the ANSI standard for flashlights is I believe a quarter of 1 lux. So lux is how intense the light is. Like right here on this table, there might be 10 lux. Okay, on my hand, if I raise my hand up closer to the light instead of 10 lux down here, we're getting maybe 15 lux. And if I put my hand even closer to the light source above me, which you saw earlier in this video, we might be getting 30 lux, okay, or 40 lux. And right next to the actual surface of that thing is probably close to 1,000 lux or so. So, compared to the 10 lux on the table, that's a big difference. So once you get further and further away, the lux gets smaller and smaller and smaller. And so like across the room, maybe the lux from this light is the 1 lux, and then from even farther from that, so further didn't I? Even farther than that, you eventually get down to a quarter of a lux. So the light over my head might have 70 meters of throw or so, and that's where it's fizzled down to quarter of a lux. This thing's quarter of a lux makes it a ridiculous distance of 2,500 meters, or 2,500 meters. And that means that at 2,500 meters at sea level, the calculation takes into consideration atmosphere. It is a myth that it doesn't. It is not based on a vacuum. It is based on the atmosphere. In fact, it's based on relatively thick atmosphere at sea level. Okay, so at sea level, and I forget the percentage of humidity, but at sea level, with the given humidity, you take it out, all right, and you have your lux. Okay, so that lux will make it, 1/4 of a lux will make it 2,500 meters. Has nothing to do. Biggest myth about throw is that it has something to do with what you can see. It doesn't. This has nothing to do with what you're able to see with your eyes. Okay, because 2,500 meters away, you're never going to see this spot come back to you for a variety of reasons. If it's the only light source, if you're doing it indoors in some kind of tunnel, all right, not tunnel, but if you could somehow do it without stars and the moon interfering, even this thing itself is going to have a beam that's illuminating the atmosphere in front of it. Okay? Which, one of these days, while I show some beam shots of this flashlight, which I want to do, I'll show that beam. But the beam itself, the air in front of you, like for the first 10 meters, is really bright. And you have to hold the flashlight farther away from yourself to try to get that beam away from your face. But otherwise, your eyes will adjust to the brightness of that beam, and that alone is enough to prevent you from accurately seeing 2,000 meters away, or even 1,500 meters away. That being said, this thing, the closer you are, the more of that lux it is. Okay, now that lux has to travel back to you. So a quarter of a lux, even if you're if you're 2,500 meters away and you point this at a surface, and you're both facing the same direction, so the user of the flashlight and then the person, they're both facing the same surface, and let's say we take this flashlight and I'm pointing it at something, and then 2,000 meters away somebody's standing right there and they're looking at that, they're going to see a quarter of a lux, right? But I'm not, because I'm holding it from so far away, and that quarter of a lux bouncing off this building is only going so far back from the building. Okay, however, distances of around a mile or 1,600 meters, there's going to be, say, 10 or 20 or 100 lux. I'm not sure what it is. Forgive me. Maybe it's several hundred lux. It's still okay. Several hundred candela or 700 lux is bouncing off that building from a mile away. Is that enough lux then for you to be able to see it? I would say the answer is yes. So the more intensity you have, the more real life throw you have. That's true. So if you grab a 1 million candela flashlight, I should be able to see the difference of throw, because a 1 million candela isn't going to go as far as 1.5 million candela. So the farther it throws ANSI is also true. But does it really mean that I need twice the throw to see twice the brightness? No, because usually when you double the brightness, you increase the throw by, say, 50%. So say 300,000 candela, for 1,000 lumens, which is roughly accurate, not perfect, you're going to have to get 600,000 candela to go 1,500 meters, which again is roughly accurate. I'm not sure exactly what the numbers are. But roughly speaking, you need double the candela to go 50% farther. So something's 1,000 meters and something's 1,500 meters. The brightness difference between those flashlights is huge. Okay, there might even be a significant difference between something that throws 2,000 meters and something that throws 2,100 meters. Because even though there's only a 100 meter difference, the difference in candela to get the calculation right is much, much higher. Okay, because of what's called divergence. The candela ratio is based on divergence, which is how fast the beam is spreading out. And it also takes the atmosphere into effect if it's a good, well done calculation. Okay, there's ways to do it based on a vacuum, which is fine, but the other thing is the atmosphere is taken into account already, because technically you're doing it in air, so the candela is already lower than it would be if you were in a vacuum, because you're seeing all those air particles scattered in the light. Anyways, so that's kind of why it takes it into effect. Okay, that's why you can't measure it. You don't want to use the optics and the LED to measure it. You want to actually do the calculation based on what a lux meter sees at a given distance. Okay, the bigger distance you measure, the higher, the more accurate, okay, you're going to have it. Anyways, so those are the biggest myths with ANSI standard. All right, and this is going to be a long video, guys. I'll probably split this up into different parts. So now we're going to go from ANSI standard, and we're going to talk about. I'm gonna cut the video right now, because whatever. I might as well do a second one. But then I'm going to talk about brightness misconceptions briefly, and then we'll go into